Among all the chess pieces, rooks have a rather simple way to move. They can either stay on their line and go right or left, or stay on their column and go up and down. We say that it can attack those tiles. Today, we'll talk about non-attacking rook placements. That is to say, placements of 0, 1, or any number of rooks, such that no rook can attack another one. Our goal is to uniformly sample a rook placement on a chessboard. That is to say, all the rook placements should have the same probability of being drawn. In a classical mathematical manner, we not only work on an 8x8 chessboard, but on an n-by-n chessboard. We study this problem for multiple reasons. Not only is it fun and visually clear, as the combinatorial problem has a clear chess interpretation, but it's also a known problem in the combinatorics literature with some algorithm that has already been proposed to solve it. In addition, solving it the way we do led us to deeper insight as we were able to extend our algorithm to different combinatorial structures with interesting ties to a certain algebraic framework. As it is a known problem, an exact enumeration formula is known for the number of rook placements. That is to say, that we have a formula that counts the rook placements. So Pn, the number of rook placement on an n-by-n chessboard, is equal to 1 over e times the sum of the infinite series g plus 1 nth rising factorial divided by g factorial, with g plus 1 nth rising factorial being the product of g plus 1, g plus 2 until g plus n. Based on this enumeration formula, we proposed an algorithm to randomly generate a uniform rook placement. The algorithm starts by generating an integer g with a distribution mimicking the enumeration formula. Once we have this g, we add to the side of the chessboard g ghost columns. Here in the animation, g is equal to 3. Then, starting from the bottom row, we place a rook in one of the g plus n 3 columns. Then, since we want to sample a non-attacking rook placement, we cross the tiles where we can't place the rook anymore. We do the same operation for all of the rows. Once the rows are all filled, we remove the ghost columns and return the obtained non-attacking rook placement. We prove that this rook placement is uniform among all the non-attacking rook placements. What makes the algorithm work is a rather simple algebraic identity. There is a way of describing combinatorial structures with the functions that are extendable in Taylor series. It is known as Joyal species theory. Within this theory, the rook placement can be encoded with the rook polynomials. Rn of x, the nth rook polynomial, is the sum of Rnk x to the k, with Rnk the number of ways to place k non-attacking rooks in an n-by-n chessboard. Here is the algebraic identity. It should be understood in the following way. The d over dx to the power of n, xn e to the x term on the left-hand side encodes the chessboard. The middle generating series encode the probability distribution of g, and the right-hand side encodes the rook placement and the ghost columns. All in all, the algorithm samples G, glues that number of ghost column on the board, places the n rooks, and extracts the rook placement, which is completely encoded within the algebraic identity. Once we understand the underlying algebraic structure that makes the algorithm work, we can identify the mutable elements and change them, which leads to random generation algorithm for different structures. Here, what we change is the operator word, d by dx to the nth, x to the nth, that is applied to e to the x. This operator word encodes the rectangular chessboard. There is an important combinatorial structure, the Ferrers board, that encodes integer partitions. A Ferrers board is a board consisting of successive lines, each with as many tiles as the previous. The Ferrers board here represents the integer partition 5, 3, 2, as there is 5 column in the first line, 3 in the second, and 2 on the last line. The interesting thing is that a Ferrers board can be encoded by a word in the operator d by dx and x. Here, w lambda is the word that represents the displayed Ferrers board. Once again, the chessboard is represented by the word of operators d by dx to the 8th, x to the 8th. The way a Ferrers board is encoded in a word of x and the d by dx operator is by starting on the top right corner of the Ferrers board and following the shape drawn by the edge of the board. A down step is translated in a d by dx operator and a left step by multiplying by x. One can check that the chessboard indeed gives our operator word, and same for lambda, our example integer partition. With this being said, we can write the word in d by dx and x associated with a Ferrers board in the following way. We can apply this operator to the exponential function. By applying the Leibniz rule for differentiation multiple times, we get that it equals a polynomial times e to the x. This polynomial is known as the rook placement polynomial. Our k lambda is the number of non-attacking rook placement on the Ferrers board, lambda with k rooks. It encodes the rook placement on lambda. And by applying our operator on each term of the series expansion of e to the x, we get a sum over g of g lambda over g factorial x to the g with g lambda, a product that depends on the shape of the Ferrers board. From this algebraic identity, it is possible to extract an exact enumeration formula for the total number of rook placement on the Ferrers board of shape lambda. With a similar enumeration formula and a similar algebraic identity, we can state a similar algorithm to sample non-attacking rook placement on a Ferrers board. Once again, the algorithm starts by sampling G, the number of ghost columns, and adds G ghost column to the left of the board. Here, G is equal to 3. Then, starting from the bottom row, place a rook uniformly in a free column. Mark the places where no further rooks can be placed. And then do this iteratively for all the rows, starting from the bottom and going up. Once they are all filled, remove the ghost columns and return the non-attacking rook placement. Once again, it is uniform in the set of all non-attacking rook placements. This sampling algorithm for rook placement can be generalized and adapted to different structures. I am working alongside with my PhD advisor on extending it to a broader class of structures, defined by the successive application of words in the operators d by dx and x applied to some function that is extendable in series. I believe that the main takeaway from this work is the importance of the link that can exist between algorithm and algebraic identity, a link that is often underexplored. Thank you for your attention. If you want to learn more about such algorithm, you can look into the paper we wrote with my advisor on the random sampling of set partition-like structures, or you can have a look at this paper where the authors generate rook placement on a chessboard in a different way.